Hi everyone, today we're going to have a look at Eulerian and semi-Eulerian graphs. You may hear of them as Eulerian depending on who you speak to. There's heaps of things to look at with this, but I thought we would deal with the traditional problem first and then work from there. Over here I have a picture of Euler. And the typical problem that we work with is the Königsberg problem. Is it possible to cross all 7 bridges in Königsberg without crossing a bridge twice? So here we have a picture of Königsberg, and if I start here, I could cross this bridge, go to here, cross this bridge, go to here, I could go over here. So if I want to cross all of the bridges, I need to cross that one, and that one, and that one, and that one, and this one, and this one, and that one. And if I did that, I would have crossed all of them. And this was a problem posed by Euler in 1736, and he's credited as the founder of graph theory and topology, and typically we will see something like that. And that's what we call a graph. Typically these problems are reduced to a graph, and the nodes that I put on are typically called vertex or vertices, and the lines between them are called edges. Now, Eulerian problems tend to fall into 2 groups, Eulerian graphs and semi-Eulerian graphs. With an Eulerian graph, it's important to travel each of these edges and return back to where you started from. With a semi-Eulerian graph, you can travel each edge and it doesn't matter where you finish. So looking at the original problem, we could create that graph we had a second ago, and I'll just recreate it quickly now that we know a little bit more about it. Point, 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 graph, graph, or edge, 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 edge. Right, there we go. So there's our graph. Ta-da. We have, 4 vertices. Let's call them A, B, C, and D. And we have 1, 2, 3, 4, 5, 6, 7 edges. Now, before we can solve the problem and use our graph theory to find out if it's possible, rather than just doing brute forcing it with some trial and error, we need to know some language. So the degree of a vertex is described as the number of edges leading from it. A would have a degree of 3, D would have a degree of 3, C would have a degree of 3, and B would have a degree of 1, 2, 3, 4, 5. If the degree of a vertex has an odd number, we say the vertex is odd. If it has an even number, we say that it's even. So there's the first thing we need to know about degrees. The second one is that a trail on a graph is a list of vertices connected by a series of edges. So we could have a trail from A to D to C to B and then back to A. If a trail finishes where it starts, we call it a closed trail, and if it finishes somewhere else, say it was a trail from A to D to C, we would say that it's an open trail. Now, specifically, an Eulerian circuit is a closed trail, a trail that finishes where it starts, that goes through all the edges. So it would have to go through that one, this one, that one, and that one. Once. I should put that in here. That traverses all edges once. An Eulerian graph, this whole thing here, contains an Eulerian circuit. So the Eulerian circuit is the actual path, the Eulerian graph is the diagram. Now, property of an Eulerian graph as opposed to any old graph is that it only has even vertices. Now, if we look at this little graph I've got up here, 1, 2, 3, that's an odd vertice. It's obviously not going to be an Eulerian graph. Let's see if it's a Semi-Eulerian graph though. A semi-Eulerian trail is an open trail on a graph that traverses every edge only once. So if it started at A and ended at C and traversed every edge, it could be a semi-Eulerian graph. Now, a property of a semi-Eulerian graph is that it has a semi-Eulerian trail, obviously, a path where you can actually traverse it only once, traverse every edge only once. And we can detect them in the same way that we can detect an Eulerian graph when they have only even vertices. We can detect a semi-Eulerian graph when it has exactly 2 odd vertices. So this one has 1 odd vertex here and an odd vertex here, but hang on, it's got 2 more. So given that it's got 4 odd vertices, it's not going to be a semi-Eulerian graph. Now, an Eulerian trail, as opposed to an Eulerian circuit or a semi-Eulerian trail, can be either of these. Any other trail is not an Eulerian trail. Okay, first problem. So here is the Königsberg graph, nicely drawn, and we can see that A has a degree of 3, B has a degree of 5, C has a degree of 3, and D has a degree of 3. And we can now determine if it's possible to traverse all bridges at once by using our little bit of graph theory that we've learnt. Is an Eulerian trail possible? Well, if all the vertices on the graph were even, we could get an Eulerian circuit. But we can't do that because, as we can see here, they're all odd. If exactly 2 vertices on the graph was odd, we could create a semi-Eulerian trail, and thus we'd call this a semi-Eulerian graph. But unfortunately, all 4 are odd. So it's not going to form there's not going to be a semi-Eulerian trail that's possible, and it's not a semi-Eulerian graph. So, given that, we know that no solution exists for this specific graph. We can't cross all of the edges exactly once without having to go back over another edge. But obviously it's possible to do it. So let's have a look at a case where we would have one of the 2. Here's a different graph. It's very similar, but I've drawn an extra 2 lines across the middle. And that's changed the degree of the nodes. So now A has a degree of 4, B has a degree of 6, C has a degree of 4, and I took out that line too. D has took out that edge. D has a degree of 2. Now, given that all of the degrees are even, that indicates to us that this is an Eulerian graph, and we will be able to make an Eulerian circuit. So let's try. If we start at A, where do we start from? We started at D, we went to A, then to B, then to C, then back to B, then back to A, then back to B, then down to C, then across to D. That way we've crossed all the edges and shown that it can be done. Perfect. So if all the vertices are even, then we have an Eulerian graph. We can make an Eulerian circuit. An Eulerian circuit is a trail. Now, if we had a semi-Eulerian graph, let's see what this one is. We have a 3, a 4, a 3, and a 2. 2 of our vertices are odd, exactly 2 in fact. It can't be more, it can't be less. That indicates to us that we have a semi-Eulerian graph. Now we can make a semi-Eulerian trail, this thing, if we start on one of the odd vertices. If we start on D, it won't work. But as long as we start on A or C, it will. So here's a case. A to B, B to C, C back to B, back up to A, across to D, and we finish on the other odd node. So whatever odd vertex we start at, we're going to end on the other odd vertex. And there's the trail there. So there's a bit of an investigation into Eulerian and semi-Eulerian graphs and a review of the Königsberg problem. I hope that was helpful to understanding how to deal with these sorts of problems. Thanks everyone.